So in order to get react with the SiO2 and Al2O3 material to create the slag, this calcium carbonate first has to get decomposed in the form of CaO and CO2. So this CaO can get react with this SiO2 and Al2O3 material for the proper slag formation during the iron ore smelting process. And we all know that the decomposition reaction of these particular fluxing materials, or we can say calcium carbonate or magnesium carbonate, is highly endothermic in nature. So it requires some amount of heat during the process. And in order to provide that heat inside the blast furnace, we have to add more and more coke material inside the during the blast furnace operations. So, if we are going to use the superflux sinter inside the blast furnace operation, so what we can see during the sintering process itself, we have added the enough coke breeze material inside the sinter material so that this calcium carbonate reaction can happen, and the endothermic reaction has ended during the sintering process itself. So we do not require the extra amount of the coke breeze material during the blast furnace operations during the iron ore smelting process. So in flux sinter, the lime reduces the melting temperature of the sinter mix, and at relatively low temperature around 1100 to 1300 degrees Celsius can form strong bonds in the presence of the FeO material. And flux generates slag with the impurities present in the iron ores and solid fuels, producing a suitable matrix for cohesion of the particles. So these are some advantages of the adding the more and more flux material inside the during the sintering process. And flux also improves the physical and metallurgical properties of the sinter, as it is creating a cohesion between the particles. So it is increasing the strength of the sinter material so that it can sustain during the blast furnace operations. It reduces or eliminates the addition of limestone in the blast furnace, thus saving the fuel needed for the calcination reaction of the limestone during the blast furnace operation. Hence, it reduces the coke rate in the blast furnace. And there are usefulness of sintering and some new development in the sintering processes. So use of sinter can, as we had already discussed, the use of sinter during the blast furnace operations can increase the productivity of the blast furnace, and at the same time it can reduce the coke rate inside the blast furnace. So generally, in the major blast furnace operating plants, they use 30 to 50% of the sinter as a feed material during the blast furnace operations. And sintering process also helps in utilization of iron ore fines, because we cannot throw them away, because they are also containing some iron rich values. And in recycling, all the iron fuel and fuel bearing waste material in the steel plant can be used during the sintering process itself. Whatever the gases is coming, whatever the preheat gases is coming from outside from the blast furnace, that can be reused back for the sintering process itself. While in the structure of the metallurgical enterprises of a full cycle sinter production represent up to 50% of gross emission. Then there are some new developments in the sintering process, like addition of they are nowadays they are using some surfactants for providing the moisturizing and or into the moisturizing liquid, help in improving the wettability of pelletizing charge. They are adding some special binding additives like polyacrylamide, sodium humate, or polyvinyl acetate to improve the pelletizing quality of the charged material. Then, for increasing the strength of granules of the sintering mixture, uh, can be improved by introducing colloidal forming additives like aluminosilicates we can add. Then we can moisten the gas flow entering the combustion zone, improve the conditions of CO after burning in the sintered layer. Then there are some other developments like use of calcined lime. Nowadays they are trying to replace the calcium carbonate. Instead of calcium carbonate, they are using calcined lime, pre-calcined lime. So it is already has been converted into the CaO. So it does not require more and more energy for the decomposition process during the sintering. Then intensive mixing and granulation systems are there. Twin layer charging they are uh, doing. Then coating granulation is there. So These are some technological advancements which are going nowadays for the sintering process. So until now we were talking about the until now we were talking about the metal oxides and how to reduce those metal oxides with the help of blast furnace or sintering operation and other things. So ores cannot be ores cannot be only found in the in the oxides form only. They can be found in the sulfides forms. Sometimes they can be found in the form of sulfides also. Like for example, copper ore is mainly present in the form of sulfide ores like chalco, for example, chalcopyrite. So in order to produce the metals from the sulfide ores, either we can go for the reduction smelting process, we can convert, maybe we can go for the like we are doing with the with the oxide processes, we are just going with the carbothermal or hydrogen reduction processes to get them converted into the metallic particle, to get them converted into the respective metals. So can we go with the same processing itself steps with the help of by using these sulfide ores? We can check. So with the help of Ellingham diagram, or we can say delta G versus temperature diagram, we can check the feasibility of the reactions for converting the sulfides ore via carbothermal or hydrogen reduction process to directly produce the respective metals. So generally this Ellingham diagram shows the stability of the sulfides as a function of temperature or ease with which metal sulfides can be reduced. So reaction closer to the top of the diagram are the unstable sulfides, while at the bottom of the diagram, sulfides are harder to reduce. So as we can see, as the delta G value is getting more and more negative, the sulfides are more stable, while the if the delta G value is in the positive range, so we can say the sulfides are non-stable at that particular temperature or partial pressure of those things. Then how to extract metal from the sulfide source. So theoretically, if we think, or if we think economically, so reducing a sulfide to metal is not practiced to any appreciable extent, because carbon is useless as a reducing agent, because most of the sulfide reduction with the help of carbon is non-feasible at particular temperatures of around 1000 or 1100 degrees Celsius. However, if some reactions are happening in some sulfide ores, if the reaction is happening, reducing reaction is happening with the help of carbon, so it will form a byproduct. Like in the case of oxide, when we are talking about oxides carbothermal reduction, it creates CO2 and CO as a byproduct. In case of sulfide material, it will produce CH2 as a byproduct material, and it can it cannot be used as a raw material in any application. Like carbon sulfide is useless, so we just have to dispose that byproduct which can form during the carbothermal reduction process of the sulfide ores. So we need to first carry out the research for the disposal of this CH2 formed during the uh, carbothermal reduction of metal sulfides. While hydrogen is useless as a reducing agent because the reduction is thermodynamically unfavorable at all, if somehow the reaction of hydrogen reduction is happening, if somehow the reaction is favorable, so it will produce the H2S as a byproduct, H2S gas as a byproduct, which is highly toxic in nature. So it is not preferable to go for the hydrogen reduction process of any metal sulfide ores, because it can create the toxic hydrogen sulfide gas as a byproduct material. While talking similarly for Ellingham, when we talk about the Ellingham diagram for the oxide material, so reaction closer to the top of the diagram are the most noble metals like gold or platinum. We can see they are majorly stable in their metal forms. So when we talk about the processing of these gold and platinum ores also, so generally they are found in their native forms only, most of the time, not in the oxide forms. While moving towards the bottom of the diagram, metals become progressively more reactive and their oxides are harder to reduce. Like for example, if we talk about the alumina, oxide of aluminium. So Al2O3 cannot get reduced by with the help of carbothermal reduction up to a temperature of around 2000 or 2100 degrees Celsius. So for reducing the temperature of the aluminium oxide for the reduction process and to produce the aluminium metal, we have to go for the electrolytic reduction processes like molten salt electrolysis process with the help of Hall Herold cell to produce the aluminium metal. So we can say it is quite hard to reduce those oxides with the help of the carbothermal reduction or hydrogen reduction process. So metal extraction from sulfides, carbon can be used only for the reduction of oxides because its affinity for H2, Cl2 and F2 is lower than that of the metal. The extractive metallurgy of sulfides consists generally of a combination of oxidation and other processes, either to obtain the metal directly or the oxide which will be reduced or the soluble sulfate which will be subjected to leaching and electrowinning process. So generally for the metal extraction from sulfides ore, we generally go with the process of the oxidizing roasting so that we can convert them those particular sulfide materials into the particular respective metal oxides, and at the same times we are creating the S2 gas, SO4 gas which can be converted into the S2SO4 material as a byproduct, and the produced metal oxide can be further reduced with the help of carbothermal or hydrogen reduction process to produce the respective metals. While otherwise we can directly go with the hydrometallurgical leaching processes for the processing of these sulfide ores, and which is very feasible according to the thermodynamic data. Then purpose of roasting. So roasting may be used to prepare sulfide concentrate to oxide for subsequent pyrometallurgical carbothermic reduction smelting operations. For pyrometallurgical processing, the purpose of roasting is also to decrease the sulfur content to an optimum level, or we can say partial roasting for smelting to copper matte in many modern processes. However, roasting is not a separate step, but is combined with matte smelting process itself. While for hydrometallurgical extraction, roasting forms water-soluble compounds that can be leached out easily, and the roasting processes which produces the so-called calcines has several effects like drying the concentrates, oxidizing a part of the iron present, controlling the sulfur content, partially removing volatile impurities or especially organic, and preheating the calcine with added fluxes like silica and limestone. So there are so roasting methods can be divided into the different parts, like there are partial oxidizing roasting process. So when we talk about CuFeS2, chalcopyrite ore, so when we are going for the partial oxidizing roasting process, so what we are trying to do, we are trying to convert the iron sulfide content inside that chalcopyrite ore into into the iron oxide. So if we are just going for the partial oxidation process, like we are not trying to convert the Cu2s into the into Cu2O material, so we call it as partial or oxidizing roasting process. While when we talk about total or dead roasting, so as the name suggests, we are going for the complete oxidation of all sulfides present in a particular mineral to produce the respective metal oxides for further hydrometallurgical operation processes or maybe pyrometallurgical operation processes. Then coming to sulfatizing roasting process, so what we are trying to do, we are trying to convert sulfide minerals into their respective sulfates. So these types of roasting is generally carried out at a temperature range of around 550 to 565 degrees Celsius to form sulfates. Like MS is going to metal sulfide is going to convert into MsO4 so that it can be further utilized in the hydrometallurgical operations or maybe pyrometallurgical operations. Then then there is a chloridizing roasting process. As the name suggests, we are trying to convert that particular metal sulfides into into respective metal chlorides, which can be easily most of the time, which can be water soluble, and we can go for the hydromagical leaching operations. Then there is chloridizing volatilization roasting. So it involves heating the particular ore during the roasting process up to 1200 degrees Celsius. So in the presence of calcium chloride, so that various metal chlorides and other volatile compounds can be separated. So as we are going with the higher temperature of around 1200 degrees Celsius, so some volatile metals uh, can go into the gaseous form, and with the help of the distillation process, we can recover them or we can separate out them from the other metals. Then for producing these roasting reactions, we have to go with some furnaces like so there are some furnaces which are generally used for the roasting operations, like first is multiple hearth furnace, which was widely used until the middle of 20th century. After that, they are going with the fluidized bed roaster processes. So the major problem with these multiple hearth furnaces were we have to go with the uh, higher size particles. Then comes the fluidized bed reactors, which are the most modern type roasters, which yields pulverous calcines. And there are two key advantages which are exploitation. So in this fluidized bed reactor, we can exploit the waste heat and high productivity in consequences of favorable kinetics. And we can go for the powder size materials also during the roasting processes, which can enhance the reaction overall reaction kinetics of these fluidized bed reactors. Then there is sintering roasters like Duetloid sintering machine for the processing of major the sulfide materials to convert them into the oxides. So this type of sintering roasters are generally used in the processing of the zinc sulfide ores to convert the zinc sulfide into the zinc oxide, and at the same time we are going for the sintering process also, so that it can be used further used during the smelting operations. Then flash smelting furnaces, which combines roasting and smelting in the same unit. So the average residence times of these various roasters varies. Like multiple hearth furnace can take a few hours for for the roasting process. Then sintering apparatus can take few minutes, while fluidized bed reactor can convert the metal sulfides into respective metal oxides in a few seconds. So these types of furnaces we have already discussed: multiple hearth furnace, then fluidized bed furnace. Then there is auto compu flash smelting furnace, which utilizes the smelting operation and the roasting sulfide to oxidation roasting operation at the uh, similar furnace, in the same furnace. So, when we were talking about the oxides, we were talking about the aluminum diagrams. So, in case of metal sulfides, during the metal sulfide, the conversion of metal sulfides into respective metal oxides or metal sulfates can be very tricky, because that can sustain different numerous composition at the same time during the reactions. So sulfide roasting is a complex process involving numerous reactions. Like it at the same times, it can decompose the higher sulfides into the lower sulfides, then oxidation of sulfides to form oxides or sulfates, then oxidation of sulfur to form its oxide, then sulfation of metal oxides, decomposition of sulfates to basic sulfates, then sulfide sulfate interaction to produce MO and SO2, then sulfide oxide interaction to produce M and SO2, formation of sub or higher oxides, etc. So these reactions can happen simultaneously during the roasting operations. And for uh, for uh, like for determining what type of reaction is exactly happening at that particular stage, we need to we need to read the predominance area diagram, or we need to make a predominance area diagram for that particular ore system. Like relevant chemistry and necessary conditions for the formation and stability of different products in metal, sulfur, and oxygen systems of roasting is treated by thermodynamic relationship or information. So at constant temperature, The stable solid phases is represented in a two-dimensional diagram using partial pressure of SO2 and partial pressure of oxygen as coordinates. And this 2D diagram is generally known as Kellogg's diagram or predominance area diagram. So for three components like MSO system according to the phase rule, we already know the phase rule P equal to C minus F plus 2. With the help of this phase rule, we can calculate the degree of freedom, and the maximum number of phases can be present at non-variant, or we can say degree of where the degree of freedom is 0. Cases is 5, or either four condensed phases and one gaseous phase can be present at the same times at that particular point if temperature is fixed. Then P equal to 3 minus 0 plus 1. So three condensed phases and one gaseous phase can occur at same times. Then the gas phase normally contains SO2 and Air2, but some SO3 and sulfur vapor may be present having two equilibrium relationships. So the composition of the gas mixture is defined by the partial pressure of two of the gaseous component. Thus in roasting, thus any fixed gas composition and temperature, the composition of the condensed phase also get fixed. So we are fixing three variables. We are fixing the gas composition of PSO2 in the form of partial pressure of SO2 and partial pressure of oxygen. And we are also fixing the temperature. So the degree of freedom will get limited, and the composition of the condensed phase also gets fixed. The stability domain of a phase can be represented in three dimensions with the coordinates temperature, PO2 and PSO2. In two-dimensional form, temperature is fixed at constant with log PO2 and log PSO2 as coordinate is used. It is also possible to plot log PO2 against temperature. So we have in these three variables, we have to fix at least one. Like sometimes we can fix the temperature, or sometimes we can fix the log PSO2 value, so that we have to deal with only two variables at the same time. So there are some examples of these predominance area diagrams. Okay, coming to next. So these are also some examples of predominance area diagram for ZNS and FeS2 S2 roasting. So they have fixed the temperature and they are varying log PO2 and log PSO2 values. So if we talk about a log PO2 value of around minus 20 and log PSO2 value of 10. So the phases present will be FeS2 and ZNS for the roasting of the particular zinc ore at 800 degrees Celsius. Now, if we want to oxidize the iron present in the system into Fe2O3, so we can see in this diagram, we have to go with a log PO2 of at least minus 8, and the temperature we had fixed around 800 degrees Celsius, and we can go up to maximum of log PSO2 value of 5, so that we can create Fe2O3 phase inside the system. While the zinc will at the same time zinc will also get oxidized in the zinc oxide forms. Then predominance area diagram of MOS. Okay, so now based on these lectures, based on the previous week lectures, we will try to solve some MCQ and some numerical problems which can help you further in your assignments. So, first one is, we had talked about the sintering process, and in during the sintering process, we were adding different raw materials inside the premix for the sintering process. So we had talked about iron ore fines, then flux and coke bleach. So we have to crush them down up to a predefined size. Like iron ore fines, we have to we have crushed them down around around 10 mm. Then flux, we have to crush it down up to 3.15 mm. And coke breeze what has to be crushed down at 6 mm, so we can create a uniform pre-mix for the sintering process. Uh, for feeding into the Dwight sintering machine. Then sintering of iron ore is done at. So it is generally done at a temperature range of around 1300 to 1400 degrees Celsius. However, if we are adding the flux material in the higher amount, that temperature can get down to 1200 or 1300 degrees Celsius or 1100 to 1200 degrees Celsius. While However, if we are going with a normal sintering process, we are not adding much more flux material inside the sintering mix. So we can expect a temperature of around 1300 to 1400 degrees Celsius for the proper sintering of the iron ore. Then carbonate decomposition process is a so it's a exothermic process, endothermic, roasting reaction, or none of the above. So exothermic process is generally defined as during the reaction, it generates the heat. If any reaction generates the heat during the processing, so it is known as exothermic process. While if any process requires some external heat for the reaction to get carried out, so it is known as endothermic process. So when we had talked about the carbonate decompositions like CaCO3 is getting decomposed into CaO and CO2 material. So the decomposition of that CaCO3 material requires some external heat for the process, for the reaction to get carried out. So this process is generally known as the endothermic process. The carbonate decomposition process is generally known as an endothermic process. And due to this endothermic process, when we are going to add the carbon flux material inside the blast